Acids and bases are specialized solutions that we talk about in class already. So let's talk about what we think about when we think acids and bases. First of all, an acid is something that's going to produce hydrogen gas when you mix it with a metal. In one of the demonstrations that we did earlier this year, we put zinc into hydrochloric acid to produce hydrogen gas. Also, when you mix an acid with metal carbonates or hydrogen carbonates, carbon dioxide is produced, in much the same way that acid rain produces carbon dioxide on the gargoyles of France. Acids tend to taste tart and sour. They turn blue litmus paper pink, and we're going to learn more about litmus down the road. In solution, they conduct electricity, and the bottom two, which will actually be the basis of our definitions about them, is that they produce hydrogen ions in water, or they're considered a hydrogen ion donor. The focus of an acid is on the H. The H itself is what makes the acid the acid. This first definition we're going to talk about is actually the Arrhenius definition. And the second definition is called the Bronsted-Lowry. And we're going to go into greater depth about those in just a little bit. Bases are the opposite of acids. They taste bitter, not that it's recommended that you taste many of them. They feel slippery and soapy to the touch. They turn pink litmus paper blue. In solution, they also conduct electricity. They produce hydroxide ions, that's their Arrhenius definition. Or they're considered an H plus ion acceptor, that's their Bronsted-Lowry definition. And they're good cleaning agents. Here we have a picture of sodium hydroxide, tiny pellets. Now a lot of people are under the misconception that acids can burn you and bases cannot, which is why I included this picture down here. This is a picture of a base burn, sodium hydroxide affecting the skin. For anyone who has seen the movie Fight Club, there's a scene where Brad Pitt pours lye, which is a very, very strong base, on Edward Norton's hand and then exposes it to water. That was a base burn as well. So just because it's not an acid does not mean it cannot cause damage to your skin. In fact, sodium hydroxide is capable of dissolving human bodies. Okay, so let's talk a little bit about the definitions of what makes an acid and what makes a base. So the first one we're going to talk about is Svante Arrhenius, a Swedish chemist. Now, he actually defined acids and bases based on the presence of a single ion. So he said that an acid is something that releases H plus ions in water. And a base, therefore, releases hydroxide ions in water. And this definition stood the test of time for a long while. So an example of, say, an acid would be something that, say, has H on the front, like this one here, nitric acid, or like this one here, hydrochloric acid. Both of these would spread out in water and produce H plus ion and an anion, H plus ion and an anion. A base, therefore, must contain hydroxide, like NaOH or CaOH2. These would produce hydroxide ions when placed in the water because it would dissociate and break apart. Arrhenius' definition worked very well for identifying common acids and bases due to the presence of those ions. However, it broke down when trying to define ammonia. Ammonia is a very common household cleaner. Works just like a cleaner, follows all the properties that we described back here for the bases, with one major exception. How is it possible that the formula NH3 could possibly produce hydroxide ions in water? Well, Bronsted-Lowry tackled that dilemma, and they redefined what an acid is and what a base is. And what they instead focused their attention on was not the hydroxide and the hydrogen ion, but it was simply the direction of the hydrogen ion. So they redefined an acid as an H plus ion donor and a base as an H plus ion recipient. So instead of having to look for two different ions, Bronsted and Lowry only focused on the hydrogen ion. Here we have a little cartoon picture of their definition in action. So if we look here, we have an H plus ion, which is quite simply just a proton. It's traveling from the acid to the base. The acid in this case is giving it away, and the base is receiving it. The acid is our donor. The base is our recipient. Now, because we have this exchange of the hydrogen ion, Bronsted-Lowry had to introduce two new terms. Because this takes place in a back and forth equilibrium movement, they had to introduce the terms conjugate base and conjugate acid. The conjugate base is created when the acid gives away a proton. And the conjugate acid is created when the base receives a hydrogen ion. So again, the conjugate base would be receiving an extra hydrogen, and the conjugate base would be created when you lose a hydrogen ion. The conjugate acid would be creating. So here are some examples. Let's see if we can follow the hydrogen ion. If you look to both sides of the equilibrium arrows that we have going on here in the middle, you see that there are similar quantities on both sides of the arrow. HNO3 is different by only one hydrogen ion from the reactant side to the product side. Though it's not as easy to recognize, water changes over here to H3O+, and that's called the hydronium ion, and it acts very, very similar to the hydrogen ion. So what is the difference from here to here? Well, the difference is HNO3 loses a hydrogen ion. Therefore, you would call HNO3 the acid. What's created as a result of giving away that hydrogen ion is the conjugate base. The acid and the conjugate base are nearly identical, save for the hydrogen ion. That means the water, to go from the reactant side to the product side, must be gaining or receiving a hydrogen ion. So if water gains a hydrogen ion, it must be the base and becomes the conjugate acid. You can pause the video now and try the remaining problems on the sheet. Identify that these two are the most similar. Here is your acid. Here is your conjugate base. Here is your base. Here is your conjugate acid. In the final problem, looking very closely here, to go from this to this, we must do what? Hopefully you recognize that you're gaining. That makes this right here, our sodium carbonate, our base, and our sodium bicarbonate, our conjugate acid. Water in this case is going to be our acid because it is a donor. It becomes a conjugate base. Water, as you've seen, can sometimes be a base and sometimes be an acid. The special term for that is amphoteric. This is a little overview of acids and bases.